Just a little bit about Sgurr, first of all. We've grown over the last 13 years from 2 staff to 200 staff, worked in 70 countries on 110 gigawatts of renewable projects, which is over a quarter of the world's global wind fleet, for example, so it gives you an idea of the scale. And we have 13 offices around the world in 11 countries. There they go, the ones in green. And that gives us very much a global context to the work we do. We also, in 2010, became part of the Wood Group, who themselves have offices in 50 countries, but more importantly, over 40,000 staff. So that gives us superb access to marine engineering expertise. Involved in projects from conception right the way through to decommissioning these days, and that gives us obviously synergies that we can feed across the business, and we cover all of the technologies. Right, the topic at hand then, and the need for performance enhancement, of course, comes from the need for cost of energy reduction. And cost pressures have always existed for wind, but they're now greater than ever. We have a maturing market, we have political pressure to reduce costs to the consumer, and in the UK we have contracts for difference coming in with competitive bids, so these pressures are greater than ever. Onshore wind faces stiff competition from other technologies, and in particular we have solar catching up fast and costs coming down very rapidly. But fortunately the timing is good, and we have new turbine technologies coming forward. We've got new measurement technologies like LiDAR, and we have an improved understanding of wind behaviour, and that all presents opportunities which can be channelled into lowering the cost of energy. How should they be tackled? Well, in various ways actually. Faster and smoother planning process has a surprising impact on cost of energy. Increased turbine size is another one, but that is in turn dictated by the planning envelope, funnily enough, quite particularly in the UK. Turbine innovation, optimised wind farm design, grid competitiveness, and grid innovation, and we are seeing some real grid innovations coming through, and cheaper finance. So really quite a variety of issues there, and for example, the UK Cost Reduction Task Force recently considered all of these, and we were involved in that process, and the outcome of that was the determination of active steps to ensure onshore wind becomes the lowest cost new generation technology of any type, not just any renewables, by 2020. There's a belief that can be achieved if certain things are done. But for today, I'm going to focus on items 3 and 4, so turbine technology innovation and optimised wind farm design, in our view that these two together can make a significant contribution to the ongoing cost reduction. We're not alone. We are seeing that owners out there are starting to put more attention to operational performance. The focus has been develop and build for the past while, but now there's a lot more up and running. We've heard some really good things already this afternoon about things being done to improve the output and performance of wind turbines, and that's been driven by owners now, and the owners are wanting to sweat their assets. They want to enhance their revenue streams naturally, but they also want to free themselves to an extent from the grip of the OEMs. And in this sector, that grip is particularly tight. We see it with all technologies, but in wind, for some reason, it's very tight. Also enhance the value at pre-disposal and acquisition, and that's where the value of output is fully realised. And the intention to date, I would say, has been mainly on reliability and OPEX, and that's absolutely fine, but this is part of the solution, and our argument would be that performance enhancement has got a lot more to deliver in addition. Well, how, you may say? Well, actually, there are a range of contributors to performance enhancement. Force restructuring, your alignment optimisation, your dynamic improvements, control and pitch optimisation, and wind farm control. And I'll go into each of these in a bit more detail. Quite a lot of that is underpinned by better measurement, and in particular LiDAR, and the way LiDAR works, and I'll not go into the details, but there is a bit of a revolution going on in wind at the moment, because we are now able, through LiDAR, to see how a wind field is behaving, not just measuring at one point and then using computer models to estimate what goes on. We can see up to a range of several kilometres what happens, and that's allowing us to optimise. Firstly, first of all, and locating turbines in trees can have advantages as a developer, reduced visual impact and shared land use, but there are implications. Reduced energy yield, the trees sap energy out of the wind, and that extends up above the canopy to the trees, to the turbine, sorry, and reduces output. Increased turbulence, an increased wind shear, and even complex thermal effects. If you're a glider pilot, you'll know all about that. But that also affects the performance of the turbines above them. But also implications for maintenance and increased failure rates and increased maintenance costs. So you have almost a triple whammy there, where you have reduced energy in the wind, you have reduced power curve efficiency, and you have increased maintenance costs. So basically, trees and turbines do not go well together. So restructuring options, well, there are things you can do is the message, and as long as you understand the effects of the trees on the wind, and that understanding is still really emerging now. But we'll have an opportunity with LiDAR to better measure and understand what's going on, and therefore refine our CFD models to make them more accurate. Then what can you do? Well, you can fell trees within the wind farm, obviously fell as many as you can. But also on the approaches, even up to 5 kilometres in certain locations can actually have a beneficial effect. Adopt short rotation to minimise the height that trees go to before they're felled, and that might involve compensation to the forestry owner, but that might actually still be good value. Felling and replanting with slow-growing species, because they take a long time to grow, a lot longer even than the lifetime of a wind farm, and switching to deciduous trees if possible, because less roughness in winter when the trees lose their leaves, and that's quite a significant effect. And all of these measures can actually support biodiversity, so it's not necessarily a bad thing, felling trees, it can be a good thing for the habitat and for biodiversity. And just to show you some information, this is from a study that we did on a wind farm in southern Scotland, and this is the LiDAR measured wind speed coming off the forestry down the hill to the left towards the turbine, and then you can see the turbine wake there. This is a CFD model without the turbine, so this is what was modelled. And after fine-tuning the CFD model, that's the level of agreement. Now, this is just a snapshot, but what we want to do is, over a range of conditions, get that agreement as close as possible, and that's what we can now do using LiDAR. Okay, moving on, and we heard a bit from Simon about yaw misalignment, and yes, we would agree there are issues there, and quite significant issues, which are, if anything, getting more difficult over time. And if you think about it, a wind vane at the back of a nacelle of a turbine measuring wind direction, it's pretty crude. It's been developed through necessity, but it's prone to operating error. It's often prone to setup error, but fundamentally, it's one point representing a huge disk, which nowadays is greater in area than a football pitch. There's no way that one point can represent it properly. But LiDAR gives you the chance now to deal with that by looking across the whole of the rotor and then accurately aligning. This is a technique that we've been developing, not looking forward, but looking backwards. So LiDAR on the nacelle, and if you look back at the alignment of the wake, when it's properly aligned, you get that. Whereas when it's misaligned, you get the graph on the right. And that difference, if it's accurately picked up, then allows you to properly align the turbine. And we have put this to the test. We've had a turbine tested in Germany now for a range of conditions. And just to show you, at this point in time, it was well aligned. So you can see the wake there well aligned with the axis at that point in time. It wasn't by about 15 degrees, and therefore 7% performance loss. And the important thing, obviously, is the spread that you get over the piece. And this was a modern turbine in a relatively stable wind flow. And look at that spread. And so that's what we've measured has actually occurred in reality with wind vane control. And we know for a fact we can improve on that significantly and therefore recover energy yield. Aerodynamic improvement, and we also see potential here. And if you think about it, as an aerodynamicist, the blade on the right would be the one that you would ideally design for your wind turbine, but that's not what you get. You get the blade on the left, and that's because it has to be manufacturable and it has to deal with structural loading. So there's a compromise there, which means aerodynamic losses. And the question is, well, is that the best compromise? And in our experience on a lot of sites with complex flows, that's not the case. And there are various things you can do. One is to attach vortex generators there, which maintain attachment of the flow to the blade, but it's how you go about it really that's quite critical to whether you achieve the performance enhancement. So our view, proportion of losses can be recovered. Vortex generators are an established technique which can be effective, but positioning is key. And for that, you need site-based tests to know that you have the optimum application of the vortex generators. But with that, improvements of 2 to 3% in energy yield can be delivered. And we have tests underway at the moment, actually, to fully prove what's achieved and the best technique for measuring it and proving it. Okay, control and pitch. And this was mentioned also earlier, and we totally agree that there are some real issues with control optimization out there. And we see some turbines which, in our view, are significantly non-optimally controlled. And the point is that real site conditions differ from design, inevitably more complex on most locations anyway. So wind shear and veer and turbulence, and because of that, control around the knee of the curve is often non-optimal. But not just that, aerodynamic characteristics can change over time. So blade roughness, leading edge erosion and so on actually mean that your optimal control should be different and it needs to adapt. So control set points and algorithms need ongoing optimization, and they don't necessarily, in standard controllers, do that. So optimized pitch control can increase production as well. And as we saw earlier, around about the knee of the curve there is quite often where you have errors which are quite insidious or difficult to spot, but they can be significant in terms of energy production, and that's where we see the most potential. And finally, wind farm control. And the point here is that wind farms should be managed as a single unit rather than a collection of individual turbines all trying to maximise their own production. If you do that, you can increase total output, but also reduce wake-induced loadings, which is significant for larger wind farms, and meet grid code and balancing requirements. And if you manage the wind farm as a power station, you can provide synthetic inertia and droop control and fault write-through and so on. Things which are not fully yet appreciated by the grid regulators, but I think that will come. And when it does, these things will have value, and therefore the ability to do that will become key. And according to real conditions and not a model. And again, if you've got LiDAR, you can do it based on real-time conditions. So I'm going to kind of finish off now with some information that LiDAR has provided that I think is quite significant. These are scans from a wake behind a turbine. This turbine was offshore, so there's no roughness effects. But two quite significant findings arising from this. One was, if you think about it, you've got an imbalance between above the rotor and the bottom of the rotor. And because of that, you can actually see here, especially there and there, almost a cascade effect as the high energy wind comes in above the turbine and down to depress the wake. And that has implications for the shape of the wake and also wake recovery, and that's not been appreciated to date. The other thing that was quite interesting was inflow to the turbine, particularly lower wind speeds, and you can see there an inclined inflow. So as the flow is moving into the turbine, it's actually inclining up the wake, which has implications for aerodynamic efficiency, obviously, of the turbines. So two quite significant findings which weren't appreciated before we had LiDAR, but now we can see them, and now the opportunity is to build them into our models and into our designs to deal with them properly. And then there are cumulative effects, and when you have turbines one after the other, here's another scan, in this case with 3 rows of turbines. And the question here, the important question, is how momentum is transferred from the wind above the turbines down into the rows to maintain production as you go through the rows. And that's, as yet, not fully understood, but that understanding is now starting to measure, to evolve on the back of LiDAR measurements. And we will have future wind farms better designed as a result of that. Just to show the locations where we've been doing work, so south of Scotland, northern Germany, also in the German North Sea, and in Norway. So all of that work has underpinned some of what I've been talking about. And finally, equally important to delivering improvements in performance is being able to measure and prove that you've delivered performance, and because of that we have quite a lot of work underway on the best techniques to do that, and in some cases combinations of techniques which allow us to establish that we have achieved what we thought we would achieve. So in summary, there are significant increasing cost pressures on onshore wind, but optimistically, further reduction is eminently achievable, and performance enhancement is an essential route to that. There is a wide range of contributory measures. A full and detailed understanding is essential. In many cases, LiDAR provides a tool for understanding, but the expertise itself is even more important, backed up by comprehensive test and validation. As an industry, we have to focus on these measures. Okay, thank you.